Okay, ANOVA stuff. So we're going to run through sort of getting the building blocks of ANOVA today. We may get to an SPSS thing that's probably ambitious, but we'll see how far we can get. Talk about effect sizes, confidence intervals for ANOVA stuff, and then follow-up tests. The follow-up tests are fairly straightforward with one-way ANOVA. Things start to get a little bit more complicated when we get into factorial designs. Okay, but to bring us, sort of ground us, all right? At this point, we talk about single sample z-tests, right? If I'm comparing some single sample to some reference point with a known population mean and standard deviation, this is my z-test. Rare that we run into these, but this is a tool that we have. Generally, what we're looking at is a single sample test, right? Because I've got some sample that I want to compare to a reference, some reference point, but I don't know what the population mean and standard, or I don't know what the population standard deviation is. So what I do is I use S as an estimate for the population variance or the population standard deviation, and use my independent single sample t-test. Independent sample tests, right? I've got two different. I've gathered samples from two different populations that I want to go through and see if they are similar in terms of the mean value, right? So I take sample one, sample two, compare those two to see if I'm getting enough of a difference between these two samples to infer an actual difference in the population value. And then our paired sample test, this is our repeated measure test. We're looking at whether or not the mean difference score across two different assessment points is reliably different than zero. Got this asterisk here because, again, wanting to think about and recognize that if I have a matched design, traditionally what we've done is analyzed results of a matched design within a paired sample test. Remember that our paired sample tests are intensely powerful. Anytime that you can incorporate a repeated measures factor into your design, you're going to be better off with stuff, okay? But what happens if we would have more than two means? To this point, we just always have two means, two different things to compare. What if I want to see whether drug A, drug B, and drug C have different effects, right? I could go through and I could, if I wanted to answer this question, if I'm limited to my t-tests, this is three separate t-tests, A versus B, B versus C, A versus C. And I could do that, right? Problem is, though, we're going to run into some stuff here. What I could do instead is I could run an analysis of variance, right? My ANOVA designs are going to provide me a tool to look at mean differences between two or more groups on some continuous outcome. So I'm interested in some outcome that I'm measuring on a continuous scale or sort of an ordinal scale with enough values for me to pretend that it's a continuous scale. And I can go through and I can run this in an ANOVA design. Notice I'm saying two or more groups. I can run an ANOVA with just two groups, right? Or I could run a t-test like a normal person. But I could also run this in an ANOVA design that's perfectly acceptable. Our ANOVAs are going to be more efficient to some extent than a t-test, than multiple t-tests. I, to some extent, avoid some complications with type 1 error, compounding error. If I run multiple tests again and again and again and again, the likelihood of me making an error on a type 1 error on at least one of those is going to increase. And then finally, this is going to give me some additional flexibility in designing experiments, interpreting results, and things along these lines. It just gives me more tools in my belt if I've got more than two different populations I wanted to look at. So our basic one-way design is I've got population 1, population 2, population 3. Okay? And so the example we've been talking about, let's say that population 1 is the population of individuals who have been prescribed drug A. This is a hypothetical population of all individuals prescribed drug B, and the hypothetical population of all people who have been prescribed drug C. Now, I can't find all the people with this illness and administer them these different drugs, and so what I do is I go through and I collect samples, right? And sample here I've got a balanced design, 15 people per group, and I'm finding that I have differences in terms of the mean score on whatever response or outcome it is that I'm looking at here. Okay. Two possibilities, just as everything else we've talked about before. These differences that we're seeing, are we ever going to get identical mean scores across these? I mean, with sufficient precision, we're always going to have some difference, right? And so again, this is why I harp on you guys about, at some point in your response, identifying that our hypotheses tests and our confidence intervals are talking about population. I'm trying to make some inference about this, right? I don't know what those are, right? All I can observe are these things, right? So I don't need a hypothesis test to see if this is different than this is different and this is different, right? Haley, are these values the same? No, I didn't need a hypothesis, I didn't need p-value, I didn't even bring p-values in it to say that these are different numbers, right? What we're trying to do with these tests is to say, do we have sufficient evidence to claim that, or to support our claim that, yes, the population mean across these different groups is likely to be different, okay? So, two options, right? These differences that we've observed as just random fluctuation. This is consistent with what we would expect with sampling populations with identical means. This is just kind of random variation that we would expect anyway, right? Or do we have enough evidence? Are these means sufficiently different to allow us to conclude that yes, it's likely that these samples were drawn from populations having different characteristics in terms of whatever mean value is. Okay? You have a question? Yeah.
Yeah, just one thing that's always confused me on ANOVAs. What's the basic difference between ANOVA and a regression? It's just the IV?
Nothing. Nothing. There is no difference. Mathematically, they're identical. The procedures, like the song and dance that we do, is a little bit different. And we'll talk about when there's nothing that you could do in an ANOVA model that you can't do in a regression, and arguably better in a regression. What's that?
When you just use regression at that point?
Well, sometimes there are certain types of things. Any ANOVA design that you have, I can evaluate that in a regression model. But if I'm trying to present this to my field, and ANOVAs are what people tend to think about and the approach that they take, and I've got discrete different groups, and I don't have any weird complications where I'm trying to control for something, or then an ANOVA is perfectly fine to do, right? And it probably makes more sense if I say there are mean differences across these groups, right? So again, thinking about that Wilkinson article, when you're talking about choosing sort of minimally complex and sort of minimally sufficient analyses, like what are the analyses that actually do what I want it to do? Let's do those, right? Because as soon as you start getting into more complex regression models, now the responsibility is on you to explain it to people and explain your results and help them understand and see how it's identical to ANOVA. But if it's identical to ANOVA and I just ran it in a regression just because I felt like being a smart guy, that's complicated things and I don't need that. But from a mathematical standpoint, there is no difference between ANOVA and regression. It's the same model. Excellent question. Other questions with this? All right. So ANOVA terminology. We talk about the different words we use. So it's sort of taking the same construct and just giving it a different name, pretending we have something different. But if we're talking about ANOVA stuff, if we're talking about our factor, this is our categorical IV, right? Our categorical independent variable that's separating the group, right? So we could say we're talking about experimental condition. We've got experimental condition 1, experimental condition 2, experimental condition 3. We could say year of high school, right? We've got freshmen, sophomore, juniors, seniors. If we're looking at multicultural research and looking at differences in response across different racial ethnic groups, ethnicity could be a category we're using. Best case scenario in ANOVA, we're looking at something that truly is sort of a category. It's a different thing, right? We start to run into problems if I say, oh, here's my continuous scale on extroversion, and I'm going to group people into low, medium, and high groups based on median splits or something like that. Median splits are terrible. It's something that people have used a lot, but this is where the regression stuff starts to come in, right? In this case, if I'm interested in the relation of a continuous IV with a continuous DV, then just use a regression model, like, because that's what that handles, right? Now, in our history, regression models were more difficult to calculate and compute, and so what people would then do is use group-based models and then use median splits or quartiles or something like that to break people in, because computationally, when I don't have SPSS or anything else, if I'm using sort of punch cards and sort of whatever, these are easier to calculate by hand, right? Today, there's no reason for that, right? But in general, if I'm running experimental design, I have this control group and this group and this group, and these are sort of orthogonal conditions, this is where your ANOVA starts to come into best play. Okay? So factor is our categorical IV. Level are the individual conditions or categories within that factor. So condition 1, 2, 3, freshman, sophomore, junior, senior, African American, Caucasian, Hispanic, Asian. These are, if these are my factors, these are the individual levels of my factor. Okay? And so our one-way ANOVA, what we're going to do here is we're going to look at the relation of a single factor with some continuous outcome, right? We can talk about this in a couple different ways. We can say, are there statistically reliable differences in outcomes across levels of the independent variable, right? So do we see mean differences in condition 1, 2, or control? We can also think about this in terms of a general GLM type of approach, a more regression-based approach. We can say, is there a relation between condition and outcome? Is there a relation between year of high school and outcome, right? And that's thinking about things in more of a continuous way, a little bit more flexible. We'll talk about that next semester about sort of the benefits of thinking about that way. But if we have true group-based stuff, group categorical differences, it's often easy because we can see groups, right? I can think about sort of this group versus that group and whether or not they differ on average in terms of some outcome. It's, for many people and in many applications, it's an easier way to think about things. Okay. Questions on terminology? All right. So why not just run a bunch of t-tests? Right? It's like, why do we complicate things? We're feeling pretty good on t-tests, right? We've sort of gotten this down, feeling, I like t-tests, right? Don't forget t-tests. T-tests are important, but remember that our risk of type 1 error, our alpha that we set, starts to increase with increasing number of tests, right? So if I have a factor with 3 levels, right? Drug A, B, and C, I could look at pairwise differences across those groups, but it would take me 3 independent sample t-tests in order to get this. I would have group 1 versus 2, group 2 versus 3, group 1 versus 3, right? And what happens is our risk of type 1 error, right? Our chances of making an error across, a type 1 error across any one of those sets of tests starts to increase, it starts to compound, right? And so across these 3 comparisons here, our likelihood of a type 1 error, saying that we have found something when there really isn't anything to find, starts to approach the number of comparisons times our alpha level. So type 1 error for this group of tests isn't alpha 0.05, right? So I don't have a 5% chance of claiming a significant effect when there is one across these group of tests. My probability of making one wrong claim when this starts to approach 0.15 across this set of tests, right? So if I say, think about this in terms of my chances of, say I've got a deck of cards, right? And my opportunity to draw a spade is what? 1 in 4, right? And so every time I go through and with replacement, with a full deck of cards, every time I grab a card, my chances of getting a spade are 1 in 4, right? What if I keep doing it? What's my chances of getting a spade across 5 draws? Is it still 1 in 4? Nope. Getting at least one of those across the succession of it, and eventually we get to a point where it's an almost certainty, right? Like it would be very, very, very weird if I drew 20 times and never drew a spade, right? This is what's happening with successive tests. Every time I do it, for every individual trial, my risk is of committing a type 1 error is 0.05, but across a bunch of them, I'm almost, if I do enough of these pairwise tests, I'm almost assured to hit a time where I'm saying, yep, there's a difference here, when it's just an artifact of just random garbage going on in our stuff, okay? And so what we can do with our ANOVA models is we look at with the differences across these groups simultaneously. We run it all in one single test to prevent this inflation of type 1 error, right? With our t-tests, I have to have two groups, right? And if I got multiple groups, I've got to put together a number of different tests, but every time I run those, my likelihood of making a false claim increases. With ANOVA, what we're going to do is we're just going to look at these all at the same time, just run it one big thing, see if we have evidence of differences across these, and we eliminate sort of this opportunity for compounding error. Okay. People understand kind of how we're sort of the logic behind this? Cool. All right. So this is kind of, this actually doesn't fix anything, and we've swept it under the rug for a minute, but we'll get into sort of how we address that stuff later. Okay. So thinking about our hypotheses, we're going to structure these the same way we structured t-tests. Our null and our alternate hypotheses. Our null hypotheses in statistical notation is going to be mean 1 equals mean 2 equals mean 3. Okay. The means of the population from which each sample was drawn are equal. Right. From a GLM approach, we could say there's no effect of our factor on Y. Okay. Again, remember that we're talking about populations. Like, these are different populations, right? Because they're different groups. They're like at least different to some extent based on how we've categorized them, right? The question is yeah, they're different populations, but these different populations differ in terms of whatever it is that we're looking for. Our null hypothesis says no. Our alternate hypothesis says at least one population mean differs from the other, okay? Data are unlikely, the data, if we reject the null hypotheses and sort of find support for our alternative hypotheses, we're saying that these data are unlikely to have occurred, assuming that the population from each one of these samples are drawn is equal to one another, okay? The thing here to remember, there's no specific alternative hypothesis in ANOVA, okay? So Laura, let's say that instead of sort of writing this out for my null, I say my alternate hypothesis is mean 1 is not equal to mean 2 is not equal to mean 3. Why isn't that sufficient to capture my alternate hypotheses?
Because it's assuming they'll all be different?
Exactly, right? But that's one alternative, right? Perhaps the population means of these three groups actually are not equal to one another, but maybe 1 and 2 are equal, but these two together aren't different than 3. Or maybe 3 and 1 are equal, but both of them are different than 2, right? And so we don't have a specific alternative like we do with single sample or our t-test, where we can say Evelyn is sort of specifying that this group is going to be bigger than that group, right? And I can test that within one single test, right? There's all sorts of different ways that these three means could be different. We're just going to go through and say, in our omnibus ANOVA design, we're just saying, are there differences? Do we have evidence of differences across these somewhere? Okay, you kind of see so what's going on with this.
So do you just write out?
Yep, just this.
That's
yeah. So I mean, don't say at least one population mean differs from the others, because on your assignment I beg, what population? I'm kind of dumb. I don't know what population you're talking about. Tell me exactly and on what, right? But we don't have like a statistical notation for an alternate, because this is one hypothesis. This is a combination of many different hypotheses, depending on how many means we're wanting to compare.
So how would you specify that? Like, the population 1 may differ from populations 2 and 3?
You just say at least average GPA across freshmen, sophomores, juniors, and seniors is different, something like that.
Okay.
So just kind of work it in. Now, this isn't to say that you can't have specific hypotheses about how those differ, right? And hopefully you do. Hopefully you've thought about this and you're not just running stuff to see what happens, right? Hopefully you have an idea for how these groups should differ based on theory and things along those lines. But from a a strict statistical standpoint for our omnibus test or not? All right, and so this is our omnibus test. This is our overall test of statistical significance. All we're testing with our omnibus test is whether or not at least one mean is reliably different from another. No information on how these means differ or change or are separate from one another. All right, our statistical tests. We're going to introduce a new distribution, a new statistical test, an F test. All right, and an F test is going to have its own distribution that's different than our T's. Okay, remember, this is why again sampling distributions, standard errors are so important. Sort of as a fundamental concept. Our statistical tests, whether or not it's Z's or T's or chi-squared, these are sampling distributions of some number that we've calculated with a specific formula. If we're thinking about from a conceptual standpoint, I would encourage you to think about things in this way. If we're thinking about our t-test, right? Our t-test conceptually is our observed difference between our means over our expected different means, assuming that the null hypothesis is true. Kate, what is this value here?
Sorry, could you repeat what you just said?
Yeah, so our t-test is our observed difference between means over the expected difference of, we would expect to see, assuming that the null hypothesis is true. What does this value represent?
Well, the null is true be 0.
What's that?
Would it be 0?
Yeah, okay, yeah. If the null, in general, we're testing about zero, testing against 0. But what is this specific number that goes down there? Think about how we calculate our t-test. Say it. Yeah.
Standard deviation?
Oh, close. Standard error. All right. Standard error. Standard error is if you want to ask anybody sort of stock answer to any question. Standard error. Ask Zach Williams about that if you notice. Standard error, right? Our standard error is the expected difference that we would expect just assuming the null hypothesis is 0, right? Assuming sort of that all of these samples are drawn from, or all these samples are drawn from populations with equal means of a given size, we would expect that mean to jump around to some extent, right? And so observed difference over our standard error, or sort of the types of differences that we would expect just sort of based on random, and if our observed difference is much larger than the difference that we would expect just due to basic sampling error or sort of sampling deviations, what do we conclude, Nick?
Can you repeat that?
Yeah, so if we see a difference of this size, and we're expecting just based on the null, if the null hypothesis is true, a difference of this size, what decision are we going to make with our statistical test? We're going to reject the null, right? I'm going to say these data, if the null hypothesis, these are unlikely data assuming that the null hypothesis is true. Assuming the null hypothesis is true, assuming that these two samples are drawn from populations from equal means, we'd expect the two means to deviate by about this much. What we've actually seen is these means deviate by this much. And so again, assuming I haven't violated any of the assumptions of the test, who's putting that in there in their response? That's excellent. You don't need to do that, but it's again something you should be thinking. Assuming that we haven't sort of decided to play by a different set of rules, this is why we would reject the null hypotheses, right? Because we're saying that these data would be unlikely to be obtained, assuming that the null is true. F-test, what we're going to do is we're kind of change things up because we can't look at a difference. We can't look at quantify things in an observed difference. What we're going to look at is the variance between sample means over the variance expected if the null hypothesis is true, okay? And so this difference, this sort of use of variance ends up being our proxy for mean differences. And this is a hard concept to get sort of sunk in, right? But we can't go through, so I've got 4 means, right? And I got 4 different groups. What's the difference between those 4 groups?
The variance.
I don't know, right? Who knows, right? Because you got there's 4 with 4. There's a lot of different ways that those 4 groups could be different, right? But I can't have 4 differences. I just need 1 difference. And so what we do is we use the variability of the mean scores to start to quantify how much of a difference that we're seeing, right? And so we've graduated from taking we've graduated from taking the observed difference in means over the expected difference if the null is true, to the variance across our sample means over the variance expected if the null were true. Okay?
So is that the range over the 4 means?
Not the range. So what we'll get here, so take a look, see. So using our variance as a proxy for mean differences, okay? We've got set 1 and set 2, right? Set 1, we've got a mean of 20, 30, 35. Set 2, a mean of 28, 30, and 31, okay? What I've got here is the variance of these 3 means and the variance of these 3 means, okay? This is just variance like I always count variance. Like this isn't a special type of variance. You all have the capabilities and the superpowers to calculate this variance by hand if you wanted to, right? This is just, I'm taking the square deviation, square the mean, sort of summing them up and dividing by, right? So this is just variance, right? But eyeballing this in this very simple set, Amelia, which one of these sets, set 1 or set 2, has a larger differences, greater differences across the individual means?
1.
Set 1, yeah. And you can look at that easy because you just look at these things, right? But if we have much larger sets or sort of more complicated numbers and things, it starts to get very difficult to eyeball it, right? And so what we can do, if we look at the variance for set 1 versus the variance for set 2, these are wildly different numbers, right? If I look at this, right, I'm not saying so this is a measure, this is a variance, which is our measure of variability, all right? Make sure, like, sort of write down somewhere in your notes. If I'm talking about variability, I'm talking about any measure of variability or range. So like range, standard deviation, variance, sum of squares, these are all measures of variability. If I'm saying variance, I'm talking about a very specific formula for variance. If I take the square root of variance, I get the standard deviation, things like that, right? But I see more variability in these scores versus variability in these scores, which is very clear in this example, means that there's greater differences across these means than there are differences across these means, right? If I only have 2 groups, this is easy. I can just like calculate the difference. But if I have more than 2 groups, what I need to do is have some method of capturing how different these groups are. And variance is a nice way to do that. As my variances, if I'm working on the same scale, there's a set of scores that have a high variance are more different, they're more spread apart than the sample with low variance. And so what I can do is I can start using variance as a proxy for global overall mean differences, okay? And so our objective at ANOVA, what we want to do is we want to start to partial out variability and assign it to different points, right? What I want to do is I want to see, are these differences, so what differences are systematic and what differences are things that are sort of just kind of random noise. And so what we do is we start to section in ANOVA, section things into between treatment variance and within treatment variance, okay? If we're talking about our between treatment variance, and treatment is just from traditional ANOVA literature. We talk about treatments. Treatment is conditions. Treatment is groups. That's just code for whatever our grouping variable is. Okay. Couple different things that can go on if we're talking about differences between groups. Okay. The differences that I see across groups can be due to systematic differences in the population. Right. I'm seeing differences in my samples because the mean value of my populations are different, right? This is systematic effects that I'm actually looking for. And plus, rolled in there, I'm probably gonna have random non-systematic differences, right? Individual difference stuff, error stuff, other noises, right? And so, within this, John, where am I seeing my between group differences in this handout? And this is, I gave this, sort of this is this ANOVA form that you have here to take it, and it's worth looking at because we'll go through and run calculations with this. But John, where am I seeing between group differences in this table?
Between, like, what do you mean exactly?
Yeah, where am I between group differences? Where would I locate those in this table? Yeah, right there, right? These are the differences across groups, right? And so in this example, right, so what I'm doing is I'm looking at learning performance and sort of number of problems solved based on room temperature. Because maybe I'm doing sort of education research and I'm looking at IO types of stuff, systematic types of things, and I might go, okay, what environmental factors start to impact performance on things, right? Because what's the appropriate temperature that I should have? Again, I'm an IO person. Anybody interested in IO or have any background in IO? Make a ton of money doing that stuff, right? But maybe I want to go through and see systematically what's the optimal temperature for an office building for in order to maximize performance. Okay. So what I'm going to do is then I'm going to say, okay, what I'm going to do is I'm going to have a group of people in a 50-degree room that's freezing to death, a group of people at 70 degrees, and then a group of people in 90 degrees. And I'm going to have them go through and I'm just going to have them do sort of problem-solving stuff or something along those lines, right? And I go through and I see differences, right? I see on average my score for the people in the 50 is 1, average for people in 70 is 4, average for 90 is back down to 1, okay? What accounts, how should I think about the differences that I see across these three means? Well, there's some stuff that can go out. Like 1, these could be differences due to like a real true effect. People really do perform better at 70 degrees than at 50 or 90, right? So it could be that, or maybe they're just individual differences stuff. Maybe this is just random stuff that happens. So I mean, I've got a sample of 5 for each one of these, but maybe this is just sort of random variation, right? Or maybe it's not random variation. Maybe it's systematic variation due to the fact that so Layla ran this person, and Kate ran this group, and Haley ran that group, and so it's not random because they're doing something that's systematically different across because I haven't trained them to appropriate protocol. So it's not random, it's systematic, but it's not anything that's due to actual difference in these populations, right? So we're seeing differences, right? But the question is, are these systematic differences driven by actual differences in the population, or are these just random noise, okay? So what I can also do is look for my within treatments error, or with my within treatments variance. Within treatments variance is going to involve our differences within groups, okay? So if I'm thinking that the only thing that's going to drive differences in terms of performance is the room temperature, right? This is a simplistic model, but it's sort of the model I'm working with, okay? Everybody in this group is getting everything identical, right? There's no differences in terms of these people, what they're getting. There's no differences in these people and what they're getting. And there's no differences in these people with what they're getting, okay? And so if the only thing that drives performance is room temperature, Haley, what should the scores of everybody in this group be?
The same.
The same. What about the scores of everybody in this group?
The same.
Yeah. And this group?
The same.
The same, right? If the only thing that is impacting performance is room temperature, then everybody who's getting the exact same thing should have the exact same score. Is that what we see? No. This is a complex behavior. There's other stuff that's going in there, right? So the variance that we see, or the variability that we see within each one of these cells is going to be what we're calling random error, right? And this error is going to be based on individual differences. It's going to be based on experimental error, things along those lines. It could be systematic differences. It could be random differences. But anything, any systematic differences that I'm seeing, or systematic variability that I'm seeing in my model that I'm not accounting for, what do we call that? If I'm not modeling it, what is it? Error, right? So if I wanted to go through and I wanted to look at differences in mass across you all, right? And I'm going to sort of base your mass on height, right? And so I say, yep, mass is based on height, right? I'm going to get a pretty good design there, or I'm going to get a pretty good effect there, right? I'm going to see that height is related to your mass, right? But it's not going to be perfectly predictive of your mass, right? I'm going to have some fluctuations. Some of you, the sort of your predicted value is not going to be equal to your actual value, and that's going to be error, right? But there's probably things that account for that error, right? What's probably, for this simple design, what's probably important for me to account for to reduce that error?
Pick your body mass index.
Okay, but that's going to be my outcome. So I'm measuring your height. What else is a relevant factor in determining your body composition and mass? Gender, right? And so gender, in my original model, anything that's due to the fact that some of you are male and some of you are female, that just gets chalked up as in the error term. That doesn't mean that it's random error. It's not random error. There's things that account for it. But in my model, it gets put in that error term because I haven't systematically modeled for it, right? So in this case, right, there are probably also things that are impacting performance other than treatment. But if I haven't modeled those things, that's getting tossed into error, right? But if I've gone through and I've taken sort of my office and randomly assigned people to different, to treatment 1, treatment 2, treatment 3, there shouldn't be systematic differences in gender or intelligence or motivation or conscientiousness or anything else across these differences, right? And so what I'm seeing here, my within group error is all of this stuff, right? And so what I'm interested in is whether or not the differences that I see across groups, my between treatments differences or my between treatment variance, is the differences that I see across groups systematically greater than the error that I see within groups, okay? Because this is just random error or variability to do stuff that I'm not measuring, right? And if I randomly assign people to condition, I should get close to the same stuff across each one of these, right? And so what I want to know is whether or not these differences, this differences that I'm seeing across treatments, starts to exceed the differences that I see within treatments, okay? So this here captures your effect plus some garbage. This here captures just garbage, okay? And so this is what I'm looking at in my F ratio. Our ANOVA, the statistical test, or our test statistic for ANOVA is looking at these two types, of the ratio of these two types of variances. I've got between treatment variance in the numerator and within treatment variance in the denominator. So here I've got my, conceptually, in my numerator, I'm saying, what are the differences that I see across groups? In the denominator, so the differences that I would expect given just due to random variation, assuming that all of these groups are being drawn from populations with the same mean, okay? We can also think about this as in the numerator, the differences that I'm seeing across groups. This is some combination of systematic effects plus is random noise over the top of random noise, right? And so I got two different scenarios here. If I have no systematic group effects, right? The populations, the samples, the populations for which I'm drawing samples really don't differ on the outcome, right? The populations all have the same mean, right? I've got no effects. I'm going to see some differences, but those differences are just due to random variation. If I take no effect plus random differences over random differences, I'm going to get an F statistic that's close to 1, right? But if I've got some systematic differences, I've got 3 different populations, and these populations do have different values, different mean values for the score, right? Then I've got actually systematic effects that's due to population differences plus random error. If I take the random error over random differences, these things cross out, I'm just kind of left with my specific effects. I'm going to get an F ratio that exceeds 1, right? And as these systematic effects start to get larger and larger, Amanda, what happens to my F ratio?
It's gonna get larger.
It gets larger and larger. Okay? So if I'm just looking at that an error, but I can't really, just looking at it, I don't know how much of it is systematic effects or error. But if I compare that to the differences that I see within subjects, the differences that I should only see, the only reason I'm seeing differences is just sort of random variability. If I take one over the other, I start to get a ratio that starts to give me a score that gets larger and larger and increasingly larger than one when my systematic effects start to overpower sort of just random variation I have in my model. Okay. How are people feeling about this from a conceptual standpoint? Feeling okay with this? Okay. So, looking at variability in my ANOVA model, here's my total variability. This is all the variability that I have in my sample, right? What I'm going to do is I'm going to section this off into two different groups. I'm going to have between treatments variance, which is going to be measuring my differences due to treatments or actual effects and just random stuff. And I'm going to section the total variability off into within treatments variance. This is going to be my error. This is stuff that's just due to chance. Okay. One thing to remember as we start to move forward into the actual calculation of ANOVA, when I'm talking about measures of variability, we have many different types of measures of variability. We have range as a measure of variability. We have sum of squares, standard deviation, variances. These are all measures of variability. When we start to get into ANOVA models, we start to work backwards and start talking and using sum of squares starts to become important, right? Recall that your sum of squares and your variance are directly related. We get our variance from our sum of squares, right? Sum of squares, this is just the sum of squared deviations from the mean, okay? I'm just taking my deviation score, the difference of every score from the mean of that group, and I'm squaring that, and then I just sum those up, so it literally is a sum of the squared deviations. Your sum of squares is a raw, very, very raw metric of variability, okay? So Evelina, I say, hey Evelina, I've got a sum of squares of 175. Does that indicate a lot of variability or a little variability?
Can you tell just for that?
Yeah, you can't tell. Yeah, I don't know, right? Depends on the scaling, right? If I'm looking at something on a scale of 0 to 1,000, that's probably not a lot of variability, right? If I'm looking at something on a scale of 0 to 10, that's probably a lot of variability, right? I don't know. So there's no meaningful sort of interpretation of sum of squares. It's just a very much a raw, sort of untamed measure of variability, right? What I can do is I can take that sum of squares estimate and divide it by degrees of freedom, and that's going to give me a measure of variance, which still isn't terribly interpretable. That's sort of essentially what we've got here is roughly the average squared deviation from the mean, which is still hard to wrap your head around. What can we do this variance estimate to put it in terms that it's easier to start to think about? What do you think, Laura?
Can you turn it into the standard error?
Yeah, not the standard error.
Standard deviation?
Standard deviation. I can take the square root of my standard, or my square root of my variance, and now I've got a standard deviation. And we like standard deviation. Standard deviation is interpretable, right? If I say the standard deviation of height is, 3 inches, I know what that means, right? I'm saying on average, scores, any two randomly selected scores in this sample of heights are about 3 inches apart, right? Okay, or any randomly selected score in this distribution is about 3 inches from the mean, right? On average, not that every score will be exactly 3 inches, but on average, that's about where it's falling, right? But standard sum of squares, standard deviation, variance, all of these are just measures of variability. And so wanting to recognize, if you recognize this and solidify this, this will start to make these calculations much, much easier, because if we start to go through and run our ANOVAs and run our post hocs and our contrasts and things like that, we're going to be using sum of squares, we're going to use variances and standard deviations. Recognizing this is all just a measure of all different measures of variability will help you kind of to see the matrix going on back there. Okay. Questions about any of this?
Is this sum of squares kind of the in treatment?
We're gonna get to that in a moment. So we're gonna have both within and between treatment sum of squares. When we get into ANOVA, our sum of squares is gonna be what we're working with. Our sum of squares and our variance are the two metrics that we're gonna be working with in our ANOVA tables. Okay. All right, let's take a break, take 10, come back, and we'll jump into calculations of these actual different models here in a moment, or when you come back. Dim lights down in front. Okay, I want to go through and again, in thinking about, I consider carefully what we do in here and sort of the relative benefit of these things. Calculating ANOVA by hand is probably not something that you'll do on a regular basis, if ever, but understanding where these components start to come from and what they mean starts to become important, because it turns out many of your projects won't be limited to just a very simple ANOVA model, and as your designs start to get increasingly complex, it's important to know where these different variance components are coming from, what they represent, because it gives you more flexibility in terms of how you're going about and sort of working through things. So in terms of the basics, calculation of our ANOVA, unlike our t-test, it's just our one test statistic. To go through, because we're working with a number of different cells in an ANOVA design, or a number of different groups, we generally see ANOVA analyses organized into a table that looks something like this. Okay, so we're going to have different variance. So this is our sum of squares, right? And our sum of squares, again, is just a raw metric of variability, right? Sum of squares for our between treatment stuff and our within treatment stuff. This is our effect, this is our error, and then just our total variability down here. We're going to have degrees of freedom, and then we're going to have a column for our mean squared, right? Mean squared variance between, mean squared variance within. Mean squared is just another name for variance. That's all it is. Like, these are like variance estimates, like actual variance estimates, like take the square root and you get a standard deviation estimate stuff. In ANOVA, we call them mean squared, which is kind of confusing. Just know that these are variance measures of actual variance. Sums of squares, variance, and then we have our f-test here. Okay. Notation, and again, if you take and are looking on your sort of handout here as we walk through this example, this will be helpful in seeing where things are coming from. Notation differs across sources. This is one type of notation. If you're looking or reading a textbook and they use a different notation, like half of this is a pain in the ass of reading statistical literatures. You got to figure out what the damn notation is corresponding to. But if you have a good understanding of what's going on, you should be able to figure that out. For our purposes, we'll talk about K as the number of levels of your factor. Okay. So how many factors do we have in our ANOVA models, or in our one-way ANOVA model that we were working on here? How many factors? How many factors? One factor. One factor. One factor, how many levels? Three. So K is going to be 3. When we get into our factorial designs, then we're going to have multiple factors. Here, just got one factor with K levels. N, this is going to be the number of scores within any condition. Okay. In a balanced design, we have the same number of people within at each level, but that's not always going to be the case. Big N is going to be our total number of scores in the entire study. Capital T, this is going to be the sum of all scores within a condition. Okay. And G, this is going to be the sum of scores for the entire study, or the grand total. Okay. So this is going to be the total of everybody within each condition. This is going to be the total of everybody in the whole study. Okay. And so this starts to become important in terms of thinking about how we're going through and calculating different pieces and parts. Okay. So if you take a look, and so this is just a reflection of what we have here. This, our sum of our x squared, this is just going to represent the sum of the squared values of all of our scores. So if I take 0 squared and 1 squared and 3 squared and 1 squared and 0 squared and 4 squared and 3 squared. Do that. This is the sum of our x scores. Again, don't get freaked out by who here's terrified of sigma. Anybody terrified of sigma? Anybody? Does sigma cause anybody anxiety? I mean, we got one honest person. It's just throw sigma at you, like scare everybody to Halloween. It just means just like add up everything in front of the sigma. Okay. So here we've just got a sum of our squared x's. Our g. This is the sum of all scores. So if I add all these up, I'm going to get 30. This is the total number of people in my entire design. 5 in each group. That's giving me 15. K is equal to 3. I've got three conditions or 3 levels to my IV. Okay. Here, for each group, I have a total. I have a sum of squares. I have the sample size for each group, and then the mean. Just working down these. These are values that are going to be helpful as we walk through the calculations. You want to know where these things are coming from, what they correspond to. Okay. Questions about this? Okay. Again, noting that within this, we're seeing variability both within and between conditions. Here is our between variability, 1, 4, 1. Here, here, here. This is the variability that we're seeing within groups, right? If everybody's getting the same thing, if everybody's receiving the same treatment, and treatment is the only thing that's driving stuff, this is just error. Differences that we see within a cell is just due to random variations, right? And so what we want to know is whether or not the differences that we're seeing on average across groups exceed just the random variation that we're seeing within groups. And if it does, then we're starting to get closer to rejecting our omnibus null and concluding that, yeah, there probably is differences somewhere in here. Okay. Do you have a good sense for conceptually what's happening with this? All right. Okay. So when we start to populate our ANOVA table, first thing we're going to calculate, you don't have to do this, but this is sort of a systematic way to go through and do it. Starting with our sum of squares total. Our sum of squares total is the total variability of scores in the entire set, right? So for everybody in my sample, what is the total variability across all scores that I've collected in this study, okay? Think about this as the full piece of the pie. Your sum of squares total is the variability, all the variability that you have to work with. This is 100% of what you have. So this is 100% of your ingredients here. Calculating sum of squares total, from a conceptual standpoint, thinking about this as the sum of each score, so x sub I sub j. This means score for person I in group j, right? So if I look at my table here, right, in my temperature condition, this is going to be the score for person 1 in group 1 is 0. The score for person 1 or 2 in group 1 is 1. The score for person 3 in group 1 is 3, right? This is what's going on here. If we go through and we take each person's individual score and we subtract it from this x bar dot dot, this is the grand mean. If we take everybody's score and everybody's squared deviation from the grand mean, this is going to give us our total variability. This is our sum of squares total. Right? So we're taking the deviation of every participant's score from the grand mean, the mean of everybody. This is our total variability. Okay? So again, sum of the squared deviations of person I in group J from the grand mean. Okay? Conceptually, this is what's going on with sum of squares total. Quicker way to calculate this, if we take the sum of our squared x values, subtract that from our grand total squared over the total number of people in the sample, this is just a shortcut to calculating this. Okay, so this is your conceptual formula. This is kind of to help you think about like what's actually going on. This here is going to be your sort of computational model. Questions here? All right. So again, think of this as all the variability in the sample. This is all of the total of the variability. This is the within. This is the between. This is all the 100% of the pie that we're going to go through and start to separate into between and within stuff. So degrees of freedom from our sum of squares total, this is going to be calculated as 1 less than the total number of scores. So degrees of freedom total is just going to be our total sample size minus 1. So in our table, if we've got sum of squares total, and we're just going to use the computational formula because it's going to be easier, we're going to take the sum of our squared x values minus the square of the grand total over n. It's going to give us 106 minus 30 squared over 15. And again, if you're pulling these just from the sheet that you can see there. With our degrees of freedom, 15 minus 1. We go through and we plug these into the table, right? So the total variability, all units of variability in my entire design is 46, right? This is all that I'm working with, and my degrees of freedom here is going to be 14. People comfortable with this? All right. What we're going to work with next is our sum of squares error, or a sum of squares within, okay? If you see within, it's the same thing as sum of squares error. This is the variability that we're seeing within groups that represents just random stuff going on, okay? So our sum of squares error, variability within each group or condition. Conceptually, what we're going to do is think about this as the sum of squared deviations of person I and group J from their respective group means. Okay? So again, if you take a look at your handout here, what we're doing is we're saying, all right, what we want to do is we want to take the deviation of each person's score, individual score, from their group mean, right? Because again, Haley, if temperature is the only thing that's driving performance in here, what should be everybody's deviation score from the group mean? 0, because everybody should have the same thing, right? But they're not, right? So what we're looking at is we're going to say person 1 in group 1, taking their score from the group mean, person 2 in group 1, their score from the group mean, so on and so forth. Then we're going to do the same thing. We're going to take person 1 in group 2 and subtract their score from group 2's mean. Go down through group 3 from their mean, and we're going to add these up, okay? So this is going to be the sum of the square deviations of everybody's individual score from their group mean. And then we're going to add these up. This is going to give us an average deviation within groups, right? And what do we call variability within groups? Error, right? It's just error, right? It's just error variance, right? Because again, if we didn't have any error and temperature is the only thing that was driving performance, everybody would have the same performance score within each temperature group, and we'd have everything figured out, right? But there's not. We're going to have variability that's due to just random stuff, systematic stuff. This is what's going on, okay? And so, again, you can literally calculate this out by taking every person's individual score from their group mean and seeing sort of what that, and sort of pulling that together into a single error term. Computationally, what we can do is we can sum the sum of squares per group, right? So if you look at your handout here, we could individually take everybody's score, their deviation score from their group mean, and add those up, or we can just look at our sum of squares here and just add 6 plus 6 plus 4, and that gives us our sum of squares within. Yes?
What handout are you?
I am too.
The temperature condition sent
I
this
just
out?
have the 2 for the ethnicity.
Okay, I handed these, you got them? Okay, we handed them out not last week, but the week before. All right, are we? Got it? Okay, cool. Yeah, just best if we were all on the same page with things. I'm gonna go through and survey people to see what I gave you and what I didn't. Sometimes I think I gave you stuff, but I just make that up in my head. I thought about it and then didn't actually do it. It turns out that doesn't actually make things happen if I just think about it. So, all right. People see where we're getting the sum of squares within. Okay. And again, this is capturing within each group or within each condition. This is capturing the variability within each group based on experimental error, individual differences, all of this. This is referred to as our error term. This is going to be important. This is going to be a huge, huge issue as we start to run through follow-up tests and post hoc stuff and contrasts. This is our error term for our overall ANOVA model. Okay? And our degrees of freedom for our sum of squares error is going to be our total number of scores minus the number of levels in each factor. Okay? So we're going to take n and subtract the total number of people we have within, or excuse me, the total number of conditions we have within each design.
So you
Yeah.
said the error term is important when you go back and run follow-up tests?
Yep, it's going to be, so it's going to be central to sort of how we go through and compute and start to put things together. So calculating our error term, we can do this easily based on the sheet we're working with here. Sum of squares per group, right? 6 plus 6 plus 4. Degrees of freedom, 15. Total number of people in our study minus the number of levels of our factor is 3, which gives us within sum of squares within of 16. Degrees of freedom 12. Okay, we cool with this?
For your total, no matter how many groups you have, you'll always do n minus 1 for your degrees of freedom.
For the total, yeah, yeah.
Okay.
And so then this is going to be changed then depending on your total number of groups that you're comparing. All right. Then we get into these are the money beats. These are the differences across treatments. This is the effect stuff that we want to calculate. And so our sum of squares treatment is going to be the variability. Variability is just a fancy term for differences, right? This is just the variability across each group or condition. And how we calculate this is going to depend on whether or not we have a balanced or an unbalanced design. Best case scenario, we've got a balanced design. Right? Our sum of squares treatment is going to be our n, which is the size of each sample, right? And it's going to be the same n because we've got the same number in each group. And we're going to multiply that by the sample mean of group J minus the grand mean. Okay? So here's sum of squared deviations of the group mean from the grand mean multiplied by the number of people in each cell. This is going to give us our between subjects treatment. For our unequal samples, we're going to have to flip this formula around a little bit. Here it's going to be the sum of the sample or the condition mean minus the grand mean squared times the number of people in that condition, and then we just have to repeat this over and over again for sort of different groups. Okay. So these, conceptually, this is how we would go through and think about calculating these. If you're doing this by hand, make sure that you've got your order of operations correct, right? So that you're squaring sort of the group mean from the grand mean, squaring that, and then multiplying it by the number of people in that group, and then taking the second group mean minus the grand mean, square that by the number of people in that group, and then adding in the third group, subtract the grand mean, square that times the number of people in that group, and then add those things together to get your sum of squares treatment. Okay, sum of squares treatment by computation, is going to be sum of squares total minus sum of squares error. This will get it to us very quickly. Okay. And so our sum of squares treatment, this is the variability that we have left after removing all of the within group error. Okay. This is going to be our effective interest in addition to some random error that we see across groups. Okay. So you can think about this as we start to, if we're calculating in this fashion, it doesn't necessarily, you don't necessarily have to calculate things in this order, but given the way this is set up for didactic purposes, what we've done is we've calculated all the variability. This is all the variability in our scores, right? And then what we've done is we've taken all the variability in our scores and we've sectioned out the within subjects variability. That's a piece or a component of the total, and we've set that aside. And in our one-way design, once we've calculated and sectioned out the variability that's all due to within subjects error, what do we have left? Yeah, our between, right? That's all that's left over in this design, right? If we section this off to our within, or our error term, everything that's left over is our effect, right? Now our effect is some combination of a true actual effect and some combination of just random differences across groups that we would see. But what we're going to do is see the extent to which this piece of the pie is bigger than this piece of the pie to see if we have evidence of systematic effects across groups. Okay? So our degrees of freedom for our sum of squares treatment, one less than the number of levels in our factor. So in this case, we've got 3 groups to our factor, 3 levels to our factor. It's just going to be number of level factors minus 1. So for our calculating over between, we're just going to take sum of squares total minus sum of squares within. Degrees of, so we got 46 minus 16. We got degrees of freedom, 3 minus 1, good to go. Questions? All right. So we've got our sum of squares, we've got our degrees of freedom, but we've got this column for mean squared. Now, as I said before, mean squared is just a different word for variance, as in proper variance, as in the variance that we've worked with all up to this point. Our goal is to look at the ratio between treatment variance to within treatment variance. Within ANOVA, we're just calling variance mean squared for reasons that are unknown to me. That's just what we do. And so what we now need to do is we've got our sum of squares, and we've got our degrees of freedom, which, as we know, is all the things we need to calculate variance, right? Remember that our variance is just our sum of squares divided by degrees of freedom. And so all we need to do to get our mean squared treatment, our mean squared error, is just take the variance, the sum of squares between group, or the sum of squares between, or the sum of squares treatment divided by degrees of freedom of treatment or between, and to get our mean squared within. Take our variance within groups is just our sum of squares error over degrees of freedom error, and we've got it, right? At this point, we're easy peasy, right? Sum of squares treatment is just going to be 30 divided by 2. Sum of squares error is going to be 16 divided by 12. And that just loads our stuff in, and we're good to go. Okay. We'll see what we did there. So this was kind of a pain. That was pretty easy. But once we got these pieces, this falls into place. All of this building up into our ratio, our F-test, right? This is our F-test, is our test statistic for ANOVA. It is just our mean squares treatment over our mean squared error. It's just the variance of our between subjects, so the variance across our means for group divided by our variance. So to think about your mean squared error, think about this as kind of like an average variance, like the average variability within each group, okay? And so if we have equal samples, and we're assuming equal variances across group, getting back to that homogeneity of variance, this is just like a nice sort of average measure of variability within condition. Okay, so if we take our effect plus random noise over the top of random noise, this gives us our F-test. And again, thinking about this conceptually as our observed differences, our observed group differences over our differences that we would expect just based on random variability of stuff. Okay, and so here, if we take 15 divided by 1.33, gives us our F ratio of 11.28. Okay. Questions about this? All right.
So
Yeah.
11.28, how would you put that in a functional definition? 11.28 means what?
11.28 is your test statistic. It is just the same functional definition as if it were your like a t-statistic or anything else, right? And in the absence of information about a F distribution, 11.28 probably isn't going to mean a whole lot. But anybody here familiar with ANOVA F distributions? Emilio, if I saw an F of 11.28, what do I think?
It's a pretty.
Yeah, that's massive. That's a huge.
3 is usually.
Yeah, right. This would be like seeing a t-test of like 9 or something like that, right? It would be big, right? But what we've got is we've got a distribution of table values that we'll go through, and then we'll go through and take a look and see so whether or not we have evidence to reject the null hypothesis.
Okay, and that's what, so the test statistic is telling me where it falls on the distribution to know if I need to accept or reject or fail to reject.
Exactly. Yep.
Okay.
Excellent question. Other questions? All right. Nice thing about calculating your ANOVA table, everything sums to 0. Everything fits, everything works together. This is a very helpful way of going through and calculating different things and also checking to make sure that everything that you've got makes sense, okay? So if I add sum of squares treatment for sum of squares error, I get the total piece of the pie. If I add my degrees of freedom treatment and degrees of freedom error, I get degrees of freedom total, right? These things add up. If I take this divided by that, I get this divided by that, I get this, I divide these two things, I get this. Everything works together, right? None of these values just kind of, you're not there. If you've done this correctly, there are no outliers. Everything is determined based on your different statistics. This is a nice way to check your math to make sure everything's sort of worked itself out correctly. Okay. So, thinking about the structure and sequence of how we go through and break down these models. Our F test is going to be our variance between over our variance within. Okay. Our variance for our between and within subject factors is just a function of our sum of squares between divided by our degrees of freedom. Sum of squares degrees of freedom. These are just variance estimates. Okay, and this starts to become important when we start thinking about calculating effect sizes and post hoc tests and contrasts and things along those lines. If we've played by the rules, there are ways to go through and capitalize on aspects of our design to maximize the power of our tests. If we start to violate assumptions, that starts to break down, and then we have to go a different route. But sort of knowing where these pieces and components start to come in starts to become important. And so sum of squares total can be separated between, within, degrees of freedom total, between, within. Everything works in a nice interdependent fashion in terms of your ANOVA models. Okay? And this is nice. This is reassuring, right? That you don't just have random values that can be anything. It can't be anything. Like if I know X and Y, I have only so many degrees of freedom, this final last thing has to be sort of what it needs to be based on computation. Okay. All right. From a general linear model, we're not going to spend too much time on this. Just thinking about if someone's outside, right? I've got a group of students outside my door, and I say, how tall is how tall is this student, right? So I've got a group of 100 students outside the door, undergraduates, and I'm going to pull one in. I'm going to say, how, and so I've got, okay, I got this person I'm going to pull in. How tall is this person? Nick, what are you going to guess?
5'9".
Yeah, 5'9", I don't know, maybe. Who knows, right? What would be nice to know if you had to make a guess?
What the population?
What the population is? Maybe more specifically what the mean of those students are at, right? Because if I know the mean of the average of the students, the 100 students that I've got sitting out there, doesn't matter. Every student that comes through, what should you guess in terms of their height? The mean. Are you going to be right? I might never be right. I might sort of miss every single time. But if I'm thinking about my success as minimizing the amount of error that I have, it should be the same number every single time, right? And so if we're thinking about your grand mean, this is your best guess, right? What's the average score of person in A in condition C? Like, I don't know. Grand mean is going to be my best guess, right? But if I start to get a group model in here, right, I start to add in some different information, right? So if X sub I sub j is sort of my expected score for any random person selected in my sample, by adding in a group factor, what I do is I say, okay, well, I'm going to guess the grand mean plus some adjustment for the group mean, right? So I say, all right, what's the group, what's the grand mean plus an adjustment for sort of how far off their group mean differs, right? And so let's say that now instead of just giving the average height of people out in the hallway, I tell you whether or not they're male or female, right? And then I give you the average for the men in the group and the average for women in the group, right? Now, Nick, is your best guess on people, randomly selected students' height, is the grand mean still your best guess? No, right? I tell you, is it a man or is it a woman, right? Now all of a sudden what I can start to do is I can take the average of the whole group and start to make an adjustment based on whether or not they're in this category or this category. And all of a sudden I start to get a more precise estimate of sort of where that is, particularly if there are large differences across groups. And so if we have sort of this component here, right, tau j, this is sort of your sort of adjustment based on knowledge of sort of their individual group level, right? So I'm sort of taking, and functionally what ends up happening here is I'm predicting the group mean, right? So now the grand mean isn't my best guess, it's the mean of that group, right? Because if this is the grand mean, and I say sort of grand mean is, say, 5'8", right? And I know the mean of women is 5'6", and the mean of men is 5'10", right? So we've got a plus or minus 2, right? So I'm just essentially saying, so for women, it's -2, for men, it's +2. If I take the grand mean +2, that's just the mean of men. If I take the grand mean -2, it's just the mean of women, right? Well, what I'm doing is I've got more information here that I can start to go through and determine, right? And if all the men, if the only thing that determined height was gender, all the men are going to be the same height, and all the women are going to be the same height, and this is going to be a perfect model, right? But this isn't the way things happen, actually, because what we also end up with here at the end is sort of an individual error term. This is the deviation of that person from their group mean, and so that's going to end in the error. And so if we think about this, we can, so the actual value for anybody in my sample is going to be a product of the grand mean with an adjustment for the group mean, with an adjustment for that individual, right? And this is your residual. This is your error term. This is the extent to which any man or woman in that sample deviates from their sample mean, right? And so what you can think about from a structural model, and Amelia, this starts to get into a more regression-based type of thing. There's snow, it's magical. We're starting to get an adjustment. We start with the mean value. Look at this looking horrified. It's Christmas. It's a Christmas miracle. So what we've got is in terms of identifying things, we don't just like sort of make random guesses. We start with the average overall, and then we make an adjustment based on our group. And then at the end, we're still going to be off by some amount, and that's going to be the difference of anybody's individual score from their group mean. That's just going to be your error term. This starts to see where we can start to see where these ANOVA models start to look a lot more like our regression models that we'll work with next semester. Okay. So you don't have to worry about this a ton. I'm just wanting this to sort of plant seeds and lay foundation for where we're headed moving forward with stuff. Okay. So want to talk about your F distribution. Amanda, this is where we're going to start taking that F score and make a determination on whether or not we fail to reject the null hypotheses. Want to think about, like, is this an expected value or not? Distribution of our F scores, right? If I were to calculate F scores based on however number of populations that we have of interest, of a certain sample sizes of a certain number, and I were to calculate F scores from an infinite number of draws from these things, I would get a distribution of F scores. Some of those F scores are going to be very large, some of them are going to be very small. This is going to determine the shape of my F distribution. Just like our T distribution, there's not one F distribution. F is a family of curves based on two parameters. Okay, it's going to be. We'll get to that in a moment. But thinking about F's as the ratio of two variances, our F values are always going to be positive. Because I can't have a negative F. If you get a negative F, you know you've calculated something incorrectly, right? Because we can't have negative variance, right? We can't have things that are in the opposite direction. Variances also always have to be positive. So I have a positive number divided by a positive number, and you get a positive number. And so we look at the distribution of F scores, always going to be positive. When the null hypothesis is true, if my ratio of observed is about the same as what I would expect just based on random variation, I'm going to get an F value close to 1. And so as a consequence of this, my sampling distribution of F values is going to bunch up and pile up around 1, right? But as my values get increasingly more and more extreme and less likely, assuming the null hypotheses, what we're going to do is we're going to get a tail that works out in the positive direction. Okay? Like our T distribution, F distribution is a family of curves depending on degrees of freedom. Degrees of freedom for F curves are going to be based on not 1 but 2 parameters: the number of groups, and sort of your within subjects here. The number is functionally the number of people sort of within the thing, within your sample, right?
So it comes from the total
Yep.
degrees of freedom?
Not my total. So your F statistic is going to be determined by your degrees of freedom between and your degrees of freedom within. So these are going to be your 2 degrees of freedom that we look up. Okay. So for our test that we just conducted, and if you look at, I had handed out last time an F table. You should have. Should not have. Oh, right here. F table, right? Just like before, like we've done previously, what we've got is you've got a table for alpha equal 0.05, you've got a table for alpha 0.025, alpha for 0.01. There are no two-tailed tests in our F test. It's just everything is in sort of the one end of things, right? And so I'm going to look, if I look at my alpha table for alpha equal 0.01, in my test that we just ran, we've got degrees of freedom between is 2, degrees of freedom error is 12. And so if I look at a critical value for at alpha equal 0.05 for F with 2 and 12 degrees of freedom in the numerator, I see that as my between. I look at 2, go down to degrees of freedom in the denominator, or my error degrees of freedom is going to be 12. I get a critical value of 3.89. Okay, people see that? Here it's 3.88 is, I guess, a rounding error on sort of one point or the other. Okay. And so this is my critical value, right? I'm saying that if I have an F statistic that exceeds 3.88 or 3.89, I'm going to reject the null hypotheses at alpha less than, or alpha equal 0.05, right? Our actual value that we got was 11.28, which is way out there somewhere, right? So John, what decision do we make based on this test?
We would reject the null.
We would reject the null hypotheses, right? We reject the null hypotheses and conclude that based on the data that we've collected, there's sufficient evidence to claim, or we reject the null hypotheses and indicate the data suggests that there are systematic differences across systematic effect of temperature on performance. Okay. Does this help with seeing kind of where these are coming from? Okay. So, other questions about our F, how you use your F table, things along those lines. Okay. And in terms of your p-values, right? So we were just talking about, like, if we were to do, sort of take this as just an up and down vote, right? Like sort of p less than 0.05, this is how we would go through and do it. We would say this is the critical value, our test statistic exceeds the critical value, we reject the null hypothesis, so on and so forth. We actually get actual p-values for this, right? And so if you go to that GraphPad calculator or whatever one you're using, and you put in your F statistic and your degrees of freedom from the numerator denominator, it's going to give you an exact p-value for whatever you're looking for. And so would encourage you to do that for your stuff. Okay. Questions on any of this? All right. One thing I want to make you aware is the relation between your F statistic and your T statistic. These two are related to one another if we're talking about an F statistic with 1 degree of freedom in the numerator. If I have an F statistic with 1 degree of freedom in the numerator, what does that tell me?
2 levels.
Yeah, how do you know that? I mean,
Because the denominator is the error.
yeah, the denominator is error, and how do we calculate our degrees of freedom for the numerator, or degrees of freedom between?
It's going to be, should be people by group.
Not people,
Right.
like, so it's the number of levels of my factor minus 1. And so if I have a degree of freedom, my degree of freedom in my numerator is 1, how many groups does that tell me I had? 2, right? And so our F, with 1 degree of freedom in the numerator, with however many degrees of freedom in the denominator, is going to be equal to the square of my T value for same denominator degrees of freedom. These two are identical, okay? And so for an F statistic with a one-way ANOVA with two levels, mathematically independent, equivalent to an independent sample T, right? So if I wanted to, anything that I could run in an independent sample t-test, I could run it as an ANOVA as well and get an F instead of a T, right? But if I go through and I take a look at an F statistic, and I want to convert it to a T statistic, if I've got only 2 groups, I can take, so that my F statistic that I get is going to be equal to the square of my T. My T is also going to equal the square root of my F, right? So if I've gone through, you run an independent sample t-test, right? And you found an independent sample t-test of 9, right? And I said, so John runs an independent sample t-test, he gets a test statistic of 9, and like, I don't like independent sample, I think you should run that as an ANOVA. John would say, well, it doesn't make a difference, that's a dumb thing to do, but I'm very, because I just have an affinity for ANOVA, and I say, I want you to go through and run this as ANOVA with 2 levels of your between subjects factor, and I want you to tell me what your F statistic is. John, do you need to go through and run your this whole ANOVA design? No. What's my F statistic going to be? 3, right? Anybody go, okay, cool, I did it. It's 3, right? These two things are related to one another, but this starts to become important in sort of working back and forth between paired sample tests and, between sample or pairwise tests and F tests and things along those lines. So knowing the relation between these two. So what is going to be critical? So anybody have a t-test or a t-table on them?
Yeah.
Okay. Amanda, tell me what the critical t value is for a 2-tailed test with 20 degrees of freedom at alpha equal 0.01.
0.01 with 20 degrees?
Yep.
.528.
Okay, who's got a calculator?
1-tailed test, right? Or double-tailed?
2-tailed test.
2.85 or 45.
Okay, Evelyn, take 2.845, is that right?
Mm-hmm.
And square that. 8.09? So if I go through and I look at my F test and I look at F with 1 degree of freedom and 20 at alpha 0.01. 20 degrees of freedom. And 1 degree, oh well, we got some, oh, that's 0.2. 8, what did you get? 8.09. I get 8.10, right? So basically we're just going back and forth with that. So if I were to go through on, say, on this F table, right? And we were just looking at this column with 1 degree of freedom in the numerator. And for each degree of freedom, I were to go through and take the square root of those values, I would perfectly reproduce the corresponding values on the T table, right? So if I take a T statistic for a corresponding degree of freedom and just square all those values, I'm just going to get an F table. So it moves back and forth between these. This starts to become important for moving flexibly around calculations. If, say, someone has, so Haley, you're interested in trying to calculate an effect size based on someone's study. And they only got two levels to their, so they're only looking at two groups, but they didn't give you means and standard deviations. But you want to know an effect size, and they, for some reason, ran an ANOVA instead of a t-test. How might you go work backwards and calculate an effect size off of that?
You can just use F, so they calculate your T.
Yeah. So I take my F, and I can take the square root of that, which would give me my T, and then I can use the T to calculate a D, right? And so I can go through it, but if I don't recognize it, sort of how all these things work together, I'm sort of lost and saying, well, I can't use that to try and power this other test because they did something funky and didn't share their descriptive statistics. But if you're savvy, you can say, well, I know how these are related, and sort of go back through and work backwards with some of this stuff. Okay. Questions on the functional relation between these different statistics? Okay. So, conclusions and interpretations, right? Null hypotheses for this example: mean of 50 equals mean of 70 equals mean of 90 are null. Our mean learning score, the population of individuals completing whatever test that I'm working at, will differ at least one temperature. We're saying at least one of those is different from at least one other one. Okay. My conclusion here might be F value of 11.28 falls within critical region or beyond critical region. Set at alpha 0.01, F criteria here. Reject the null hypotheses. Conclude that learning scores across these populations are different in at least one temperature condition. Results suggest that room temperature has a statistically reliable impact on learning. And we'll kind of see how we translated our omnibus test into an interpretation here. All right, cool. Questions on where we're at, what we've done up to this point? Yeah, Evelina.
Can you determine which scores they are mistaken?
Not based on your omnibus test, all right? And this is where we start to get into how do we, so okay, we know there's a difference in there somewhere, but is that the end of the story? Probably not, right? And so this is where we have to go through with follow-up stuff and try and start to tease things apart, okay? So, effect sizes. Couple of, oh yeah, John.
I just say quickly the interpretation, so then as well there's no like directionality to it, at least like so far.
No directionality. I'm just saying there's a pony in there somewhere, right? I don't know where it's at. It's just like the data suggests that somewhere at least one of these things is different than one of these other things. Now, depending on how different things are, you might be able to eyeball your group means and have a good guess on where things are at, but then that starts to become problematic in terms of error, right? So this is where it's always, always, always better to have on the front end written down concrete hypotheses on how things are going to be different, as opposed to just saying maybe they are, right? That's where we start to get into problems with selective attention to certain pairs of means and things along those lines. All right. So effect size for our one-way ANOVA, a couple of different ways we can calculate stuff. First is going to be what a metric or a statistic we'll call eta squared. Okay. Eta squared, pretty easy to calculate. Eta squared is just going to be our sum of squares treatment over our sum of squares total. And Nick, if you're looking at sum of squares treatment over sum of squares total, any guess on how you might interpret eta squared?
How much your between groups varies differs from the overall rating?
Close, right? Thinking about this in terms of a ratio, eta squared tells us the proportion of variability in our outcome that's attributable to our IV. Think about this as an R squared value, right? For these data, right? Our temperature factor is accounting for X percentage of the total variability in performance scores, okay? And again, this is where looking at the calculation of these test statistics can start to help you get a good sense for what these mean literally. Literally, we're taking the percentage of variability, the variability that's associated to our between subjects effect, over the total variability. So this is just a ratio or a proportion of the total variability that's attributed, that we can attribute to our grouping variable based on the data that we've collected. Okay. We can also calculate eta squared or estimate eta squared based on our test statistics. Shut up, crows. You're worse than that cracker. We can also calculate our eta squared based on test statistics. So, if, and this often happens, we don't often have access to our sums of squares if we're looking at someone else's publication. But we can also, if we have degrees of freedom and the F-test, we can go through and approximate your eta squared. For your stuff, do this, right? This is just an easy way to do it, but you can reverse engineer some stuff there, right? Judge McClellan have also proposed interpreting eta squared as percentage reduction in error, right? So this is all the variability. So this is the percentage reduction that's accounted for by this known factor that we've modeled in, okay? Think about this as a percent by which error in our prediction has been reduced by knowing what condition someone is in. Okay. Now the thing is that eta squared, okay? It is a nice descriptive statistic for what's going on our in our sample, right? And so if we can say, in the variability that we observed in this sample, this is the proportion of variability in the sample that we can attribute to this grouping factor. Okay? The problem is we know that our eta squared value is going to be positively biased. Okay? That means that if we're thinking about a measure of the actual population effect, eta squared is not a good one because it tends to overestimate the proportion of population variability that's attributable to our grouping factor. Thinking about this, any guesses on why eta squared is problematic in terms of being positively biased? So we're talking about a proportion of variability, right? And if we think about our D statistics can be positive and they can be negative, right? Can this be negative? Nope. What's the lowest value that this could be? 0. And just on average, is your sum of squared treatment going to be 0? Probably not. It's probably going to be something. It's going to be some value. So even if the population effect is 0, we're always going to systematically overestimate it because 0 is a very precise estimate. That's one of an infinite number of values that that this can take on, right? So this is always going to be positive to some degree, and so eta squared is going to be a positively biased, problematically biased. So it's a nice descriptive of our sample, right? We can say in this sample, we can say 20% of the variability in our outcome is attributable to temperature, right? But in terms of being a good estimate of the population parameter, which is what we should be interested in, is bad because it overestimates systematically, okay? And so what we can do is we can calculate omega squared. Omega squared is going to be a better population estimate, okay? In calculation of omega squared, we're going to take our sum of squares treatment minus k minus 1 times our mean squared error. Make sure your order operations are correct. You multiply that before you subtract that over the total of your sum of squares total plus your mean squared error. This is a nice conceptual interpretation. That's difficult, right? But what you can do is interpret this as your estimate of population variance, right? So this, your eta squared, is going to tell you in these data, in the data that we've collected, our sort of grouping variable, sort of in this case, let's say we get an eta squared of 0.2, right? We would say that for these data, estimate that temperature condition accounted for approximately 20% of the variability in learning scores, right? But we know that's going to be problematic, right? And so I calculate omega squared, and let's say I get an omega squared of 0.15, right? Here, I would say calculation of omega squared suggests that approximately 15% of the variability in performance scores, or say calculation of omega squared suggests that in the population about 15% of the variability in performance attributable to room temperature or something like that. Again, here identifying this as a population estimate, whereas this is based on sort of what we've actually observed in the data, okay? And your omega squared is going to be systematically lower than your eta squared to some extent as a function of your sample size. Yeah.
So omega squared is based off, or you just said it's a population estimate, so
Yep.
we're not going off of observed scores?
Well, it is. I mean, but it's just we have to use observed force scores to calculate this, but it's a better representation. Omega squared is still going to be positively biased, but much less so than eta squared. Okay, so we're just saying eta squared is not a good population estimate. Eta squared is a positively biased statistic. It systematically overestimates the actual population value, right? So it's fine as a descriptive for what's going on in these samples, but generally I'm interested in looking at the population value or a good estimate of the population values, and this is where omega squared is going to come into play.
So
yeah.
when would we use the eta squared? Like in our write-up, like if you're writing a description about your sample, you would use
You'll
that?
see this, and this is common. This is probably going to be a better estimate. And sort of like, to some extent, there will be times where we could go through and use this. But you should be thinking in terms of reporting. You should be thinking about reporting omega squared.
Okay.
Another important effect size to be aware of is F. In terms of calculating power, F is going to be the effect size that you're using. This is what's going to, G power is going to ask you to provide F, okay? F is going to be calculated as eta squared divided by 1 minus eta squared. Take the square root of that, right? We can back translate and calculate eta squared as your F, not your F. This isn't F like statistical test F. This is just effect size F. As F squared over 1 plus F squared is going to give you eta squared. F important for the calculation of power, but F doesn't have much interpretive value as a metric. It's just, we have benchmarks for small, medium, and large F, but my problem with F is that I can't give you, I can't give you a literal interpretation of F. I can't tell Emilio, oh, I have an F of this, and this is what that means. I can say, I can give you eta squared and say for these data, my grouping factor accounts for about 15% of the variability of my outcome. Or I can say my best guess for population effect is that sort of grouping variable or grouping factor accounts for 10% of the variability in our outcome of the population, right? That means something. I can sort of understand what that happens. F, I don't know how to make it a meaningful conceptual interpretation of F outside of this is what small, medium, and large. But F starts to become important in calculating power, so you need to know what it is and how it's going through calculated. Okay. So again, interpretive standards for eta squared and omega squared, small, medium, large. F, a little bit different, small, medium, large. But again, sort of one in base. For your write-ups, think about using omega squared and sort of recognizing sort of the difference between eta squared and omega squared in terms of the interpretation, sort of the function and kind of what's going on with that. Yes?
Could you report F in addition to omega squared, or would you pick one or the other?
Yeah, you probably, I mean, F, what you should probably do is report enough information so that if someone wanted to calculate F, they could. But in terms of a functional interpretation of an effect size, omega squared is going to be your best bet for a one-way ANOVA design. Okay. So this starts to get into a little bit different, sort of different families of effects, right? To this point, we've been talking about D's and G's and glasses delta and things along these lines. These are measures of sort of between pairwise effects, right? Here with eta squared, omega squared, when we start to get into multivariate effect sizes, we're talking about proportion of variance types of effect sizes, okay? Now I can sort of go back and forth, right? But if I'm talking about a between subject effect, or excuse me, a pairwise effect, D, G, that family of effects is nice because it says, yeah, this group is scoring roughly, you know, 3/4 of a standard deviation below this one. Right, that has some X% of variability in my outcome that's still kind of meaningful, but not as meaningful for a pairwise effect as talking about sort of the actual difference between those groups. When we get into ANOVA or omnibus tests where we have multiple groups, then it starts to become hard to say, oh, this is the exact difference, right? And so we start to talk about things as a proportion of variability. So think about these as basically an R-squared value for ANOVA. Getting back to this idea that they're functionally the same thing. Think about this. This, in actual fact, if you're familiar with regression models, this is your R-squared, this is your adjusted R-squared. Questions? All right. Confidence interval for your effect sizes. I used to be jazzed about this, but I'm less jazzed now. And mostly I was just excited because I figured it out. But something to be aware of if we wanted to calculate an effect size around eta squared. Now there's confusion in the literature on whether or not there's writings that suggest omega, this is how you calculate effect size around omega squared. I suspect that's not accurate. I think the point estimate is probably your eta squared because the values that's going into getting an upper and lower value on your non-centrality parameter are the same values going into the calculation of eta and not directly and not omega. So your effect size is around eta squared. If we wanted to do this, we could go through, pull up our Psych calculator, right? And all we need to do is instead of a T and our 95% confidence interval, what we're going to do is we're just going to switch our distribution over to F, plug in our F value. That's, yikes, I don't know. So, you know what F value I was working with there is big. Plug in our F value from our ANOVA, our numerator degrees of freedom, denominator degrees of freedom. And here, we're going to calculate 90% confidence intervals instead of 95% confidence intervals. Any guesses as to why we might calculate 90% confidence intervals around eta squared as opposed to 95% confidence intervals? Yeah.
To adjust for that positive.
Exactly, right? What we've got, right, if I'm calculating a confidence interval around my D, right, I can sort of be negative in this direction, positive in this direction, right? And sort of really splitting this into both ends, right? But for omega squared, I can't have negative variance. I can't account for negative variability. I can only sort of go in the opposite up direction. And so what we do is we would then go through for convention is 90% confidence intervals for eta squared, omega squared, because we're saying, well, we're just taking that sort of that all of that and we're just putting it in one tail because we're not worried about sort of the under, we're worried about the over. And so if we're going through and doing this, calculate, putting our F, should make sure our distribution is in F, our test statistic, degrees of freedom, 90% confidence intervals, then compute, and then I'm going to get an upper and lower limit for my non-centrality parameter. Oops. And then sort of just plugging that into this for my upper and lower. It's going to give me my point estimate is going to be eta squared, so not omega squared, it's probably eta squared. And then this is going to be a 90% confidence interval where this is the lower bound, this is the upper bound. Okay. So is a 90% interval going to give us a wider or a tighter interval estimate than a 95? What is it?
Wider?
Okay. are giving myself more or less opportunities to be incorrect? Yeah, right? Think about this from a t-test. Is a t-test for alpha equals 0.10, is that a smaller value or a larger value than 0.99? It's smaller, right? Because I'm saying, I'm willing to be, I'll give you more, if you say, oh, hey, give me a guess on this, but I'm fine if you're wrong 50% of the time, I was thinking to get pretty precise, right? Like, oh, okay, so this is what I'm gonna be, right? If you say, oh, I need you to be right 99% of the time, you give a much wider estimate, Becca. Or, okay, so yeah, 99% of intervals are gonna fall, point estimate's gonna fall within this value, right? So you're gonna get a smaller estimate on the 90% confidence interval, or a shorter interval on the 90% interval than you would with a 95. Questions on this? Yeah, John.
So then would we also use this if we wanted to calculate an effect size around omega squared? Or is that
And this is where it gets really tough within this literature. Calculating confidence intervals on effect sizes are complicated for all the reasons that we've talked about, right? And what ends up happening is we calculate our interval estimate based on our test statistic, but just like with our paired sample test, we need to make sure technically we can get an estimate, right? So we can get sort of an interval estimate based on our test statistic. And our interval estimate is going to be the interval estimate, right? What we want to do is make sure that the point estimate matches up with the interval that we've calculated, right? And so thinking about if I'm calculating a confidence interval around, at least with this procedure, calculating a confidence interval around my effect size, and I mean Steiger will give me upper and lower bound, and I can reverse engineer those to an upper and lower bound for D or for my effect size. The question then becomes, what effect size is this an interval for, right? So for an independent sample test, probably an effect size for your hedge is G, right? Using your pooled variance estimate, because your pooled variance estimate is the variance estimate that's going into calculation of your test statistic, which is going into calculation of your upper and lower bound for your non-centrality parameters, right? So in the between subject test, I could sort of give Glass's delta as a point estimate and then calculate based on my pooled variance estimate that went into my T. And it's probably gonna fit, and I'm probably not gonna have a problem. But what I'm doing is I'm giving a point estimate that isn't actually, this isn't the interval around my point estimate. Now, if I'm using Stata will go through and calculate a confidence interval around delta, or unbiased G or G, but what we're doing with hand calculations, that's probably best thought about as sort of confidence interval around hedges G using your pooled variance as your standardizer, right? Now, if I transition over and talk about my paired sample test, right? Let's say I use D average as my standardizer, right? So I'm saying this is my estimate of effect. If I go through and I calculate my confidence intervals around D average using this procedure, I'm likely to end up with a point estimate that doesn't fall within my confidence interval, right? Because my value that's going into my confidence interval, or my upper and lower for my non-centrality parameter, is my test statistic for my paired sample test. And what's the variance estimate used to calculate the test statistic for my paired sample test? Is it variability at time 1, variability at time 2? Nope. Standard deviation, the variability of the difference scores, right? And so what I've done is I've calculated a point estimate using a completely different estimate of variability than what's actually going into my test statistic, right? And so for your paired sample test, I've got a point estimate for my D average of 0.3, for my lower bound for my interval is like 0.4, because I haven't matched everything up, right? So here, when you go through and you look at the literature, it'll talk about this is a procedure for calculating confidence intervals around omega. But what I suspect that's probably not the case. This is probably actually eta squared, because eta squared is the sum of squares between over sum of squares within. That's what's going into calculating your F test. It's then getting plugged in to calculate upper and lower values here. And so this isn't something I've figured out yet, because sort of the literature is a little bit spotty, right? And it's technicalities that are sort of better suited for real quant scientists than sort of amateur people like me. So, but for the purposes of this stuff, this is how you would go through. I would probably report this as confidence intervals around eta squared, although there's some confusion in the literature. Or at least I'm confused about the literature anyway. Questions? All right. Assumptions of our ANOVA models. Formal assumptions. Homogeneity of variance, okay? And we start to get into this as identical. If we're talking about in a regression framework, we're talking about this as homoscedasticity. In a means-based framework, we'll talk about this still as homogeneity of variance assumption. Basically, just like in our paired sample test, we're assuming our homogeneity assumption is that the variance in population 1 is equal to the variance in population 2, right? We expand this out for ANOVA, and we're saying that for these data, the variance of population 1 is equal to the variance of population 2, is variance equal to the variance of population 3. We're saying that, one, not only under our null hypotheses, we're saying that the means of these populations are identical. Our assumption of our test is that the variability in each one of the populations is also identical, okay? And this starts to become important too, because remember that our error term is an amalgamation of variability that we saw within each group, right? But if we're working with populations, if we're drawing samples from populations with widely different variability, it becomes much more difficult to know what to make of that error term, right? Because it's an amalgamation of variability from populations that have different variability. And so formally, our assumption with our ANOVA model is that not only under the null hypotheses are we pulling samples from populations with equal means, we're assuming that those populations also have equal variance. So, so we're saying because this variability, because we're talking about within group variability, and what do we refer to as within? What do we label within group variability? Error, right? And we're saying our error variances are identical, right? And so this starts to become how this starts to link back in. So we don't talk about within subjects variability a whole lot in regression. We talk about error variance, right? So we're saying that our error variance is equal within each one of these populations. If we violate our homogeneity of variance, we say we have heterogeneous variances, or we have issues with heteroscedasticity, is something that we would think and talk. This is how we would talk about it in terms of a regression framework, but it's all the same thing. It's not different. It's just different names for the same type of concept. So again, we're assuming normality, but again, just as within our other means-based test, the assumption of normality involves the distribution of sample means, not the observed scores, right? So just as before, I really don't care. My concern isn't with the distribution of my actual observed means within reason, right? If I've got a small sample and scores that are way out, then I start to become concerned with that. But in general, the assumption of my test is that the distribution of sample means within each cell is approximately normal. And what are the conditions under which our distribution of sample means start to become normal? What's one? Sample size. As my sample size starts to get increasingly large, as my sample size gets larger, the distribution of my sample means starts to become normal very quickly. And what's the second one? It comes like whatever I'm sampling from comes from a normal distribution, right? So I might have my observed cells, I got 10 people per cell, and I got weird kind of boxy distributions that don't look all that normal, right? But if I'm measuring something, say neuroticism, extroversion, some type of thing like that, right? That I'm assuming has a normal distribution in the population, I'm not too concerned about that, right? My main concern with small samples is if I start to get weird skew or stuff like that that's going to start throwing, or weird outliers that are throwing things off, or if I'm, say, measuring cocaine use, right, in undergraduates, I'm expecting that's probably not a normal distribution of things, and I'm working with samples of 10. Now all of a sudden I have a problem because, one, I'm pulling from a distribution that I don't think is normal, and also my samples aren't large. And so now all of a sudden, that would be something where I would start to have concerns about violation of my normality assumption here. But with sufficiently large samples, sufficiently large cell sizes, I got a lot of flexibility here, right? Because I could have wacky looking distributions, but I'm assuming as long as I don't have extreme values that start dragging my mean around, I'm going to assume that the distribution of sample means is still going to approximate normality very quickly if I've got reasonably large cells. Okay. And again, because we're talking about variability of scores around a group mean, and our variability of scores are a measure in at least an ANOVA of error, we can also talk about this as normal distribution of errors, right? And again, this starts to get into some of the regression stuff that we'll get into later. Okay, independence, we're assuming that our observations and our errors are independent of one another. This is a between subjects design, again, so all of the scores that I get from men should be independent of all of my scores that I get from women. People shouldn't be looking on each other's papers or anything along those lines. Everything should be independent of one another. Okay. Informal assumptions, that we don't have outliers, and we're assuming informally that we have a relatively balanced design. Our formal calculations, or our classic calculations, are assuming equal numbers of people within each cell. We can tolerate some differences. Actually, we can tolerate quite a big difference in terms of unbalanced design, but it starts to make things more complicated, and it starts to make our analyses less robust to different types of violations. Questions on this? All right. Impact of our violations of assumptions. As with our means-based tests, our t-tests. T-tests are fairly robust to violations. ANOVA also fairly robust to violations. We can tolerate a lot of garbage and still have reasonable confidence in sort of what we're measuring. Okay, so again, ANOVA is relatively robust to violations of normality in our observed scores. We can have weird stuff, right? So my dissertation, I was looking at sort of ratings of amusement in response to different types of film stimuli, some positive and some negative, right? If you ask people how amused they are in response to negative stuff, what types of scores do you expect to get on that outcome? Everybody's kind of piled up around 0 because Beck, no, you showed me something that was sad. I don't think that's funny at all. But some tails and stuff like that, right? But if I've got cells of close to 50 people, I'm pretty robust to that, even though as long as I don't have, and then we're using Likert scales where we got scores range from 0 to 8. Like you can only be so high. So even if you're a weirdo and you thought that sad film was super funny, we got 50 people in there, your score is not dragging things out too much, right? So we're pretty robust to observe violations of normality, assuming reasonable sample sizes, cell sizes, and violations of homogeneity of variance, not terribly problematic. If our distributions are, again thinking about this discussion with t-tests, if our distributions are similar in shape and the ratio of the largest to smallest variance doesn't exceed about 4 to 1, okay? So if we've got, so everything's kind of looking at this, we've got violation of homogeneity of variance, right? But it's not huge, right? The 4 to 1 is a big difference, right? So this is sort of 20 to 80, right, in terms of our variance. That would be a pretty massive distinction. And the shape of our distributions are all kind of looking about the same direction. We're pretty robust here. Where we start to get problems, and this starts to come up in your screeners, okay? Also, should mention, on your set 5, I went through, made comments on your screening and sort of highlighted things. But this was your first screening out of the box. I didn't take off any points, so this is kind of maybe one of the more difficult things that you're asked to do in this class. But do go through, take a look at your screenings, make sure that you're making notes and making adjustments on the next set, so that, because then I'll start taxing you and stuff. But when we're going through and we're looking at screening for our ANOVA models, any violation of independence, right? If this group is not completely independent of that group, we've got problems, right? We need to have everybody separated. This is a design issue. But if our individual groups, the distribution of scores in our individual groups have different shapes and unequal variance, right? So condition A has a crazy positive skew, and condition B has a normal distribution, and the variability in this group is widely different than the variability of that group, that's a problem, okay? If we have unequal variances and unequal sample sizes, right? I've got 20 people in this group and 120 in this group, and this group has much smaller variance than that group, then that's a problem, okay? Violations of normality and small sample sizes, right? I'm measuring cocaine use and opiate use and 10, 12 people in each one of those groups, and my observed scores are crazy sort of skewed. That's going to be problematic, right? Because my distribution of sample means it's not going to be normal. I violated normality, and so that starts to have impact on my inference, okay? So just like with our t-tests, we're pretty okay in terms of our screening if we make sort of one violation. But as soon as we start doubling down on violations, this is where we start to lose confidence in our statistical tests, okay? To John, this is where, yeah, we might see a difference or fail to see a difference, but I don't know if it's because there is no difference or because I just decided I'm a maverick and I just decided to play by my own rules, and so now my results don't mean anything because I've done something completely different, right? So one of the things we can do is we can use an adjustment known as a Welch procedure. If I have cases, a situation where I have unequal samples and unequal variances. For you experimental folks, you do a much better job of running clean experiments, right? Where, like, oh, I'm just going to randomly say 40 people go into this condition and then only 10 go into that condition. It doesn't make any sense, right? For us clinical folks, sometimes I might only have 15 people in my eating pathology sample and everybody else scored not, so they're at 50, right? And variability here is massive and variability here is, so we need to do something, right? We can't just pretend like we didn't violate all these assumptions. Welch's procedure starts to address this and starts to make corrections. It provides a correction to your F value and your degrees of freedom. But always important, remember, with any statistic, any type of correction, it doesn't make the problem go away. It doesn't make it disappear. It doesn't fix it, right? It's not like, oh, this never happened. We've still got data where we've got violations in sample size and differences in the variability of stuff. You should be attending to these types of things, right? Because this tells you something about your data, right? If this group has wildly different variability than this group, that's probably something important. Don't treat that as a nuisance, right? There are sort of like, oh, well, we've got a violation, so we're just going to use this corrected test and it's going to make it go away. One, it doesn't make it go away, right? And there are consequences. Oftentimes our threshold for corrected statistics is higher than it would have been if we would have had everything sort of playing by the rules. But then two, it probably also tells you something important about the phenomenon that you're interested in, right? So I'm looking at people who are in this group versus people who are in that group. And I see people in this group, so the group of interest, variability in scores is way much larger than my control group, right? That's probably something important to start to take into account and start to think about, right? So Haley's doing a study Haley, you're doing a lot of studies today. Sorry, my line of vision, right? But here's a sort of report of confidence in guilt for people receiving standard jury instructions, and then we've got some adjustment, and so we're measuring the same thing. So we see, oh, there's a difference. We also see much more variability in terms of sort of where people place their confidence in guilt based on these instructions than this, right? Well, yeah, we can say that changed, increased or decreased confidence. We also got a whole other parameter going on where sort of across individuals, they're much more spread out, right? That probably tells us something important about the phenomenon of interest as opposed to just saying, oh, this is a nuisance factor, I'm going to use Welch's procedure and that's going to fix my statistics. The increased variability as a consequence of these changed scores might be more important and far more interesting than the extent to which it actually changed confidence scores, right? If I tell people this, it explodes their sort of ratings across stuff, whereas over here, everybody kind of seems fairly consistent, right? So you might find that, well, on average, if I implement this manipulation, I don't see any real difference in terms of the mean level. What I do see is a massive increase in the variability of scores, or maybe a massive decrease in the variability scores. Maybe under normal conditions, people kind of all over the board. If I change these, it doesn't change sort of their overall level of sort of thinking about how guilty somebody is, but it really brings in that distribution, and everybody's kind of online on the same thing. That could be a very good thing or a very bad thing, I don't know, right? So these are the types of things as you're going through and running your screening, right? Screenings are a pain in the ass, and it takes far more time to run the screening than it actually does the test. But thinking about what's happening in your data, what's going on, what are these characteristics, and what does this mean relative to the thing that I'm looking at, and saying, okay, is this a nuisance thing, or is this something that's maybe an important thing to start thinking about, could lead to additional ideas, thoughts, more specific hypotheses on things, okay? All right. Reporting F statistics, this is sort of examples of how you might go through it and do some stuff. We made good headway today. We'll start on Monday, or excuse me, next Wednesday with walking through